Day 129 Notes Pre-Calculus. As we continue to work with our trigonometric functions, we start learning about different ways to rewrite these functions. In fact, this week we've already learned about different ways that we can write angles in terms of coterminal or reference angles. Those will be helpful for us to recalculate particular trigonometric ratios. Well, sometimes it's nice for us to rewrite the functions themselves in different forms. Now, we already know about a handful of these identities. For example, cosecant is known as the inverse of sine, secant is the inverse of cosine, and cotangent is the inverse of tangent. We've already learned about those as definitions from last week. What might be a little bit less obvious, but just as important, is the definition of tangent and cotangent in terms of sine and cosine. If I sketch a quick triangle here with an angle measured theta, actually let me put it in the same orientation we're used to seeing it. So with theta down here, this would be our opposite side, and this is our adjacent side down here. Now, we're used to seeing this point P on our unit circle with some x and y value associated with it. So x is the direction moved horizontally, y is the direction moved vertically. While r was defined as the ratio of the circle created, we learned that sine of this theta, while we're thinking of it as opposite divided by adjacent, is simply equal to y divided by 1, since our r value is always 1 when we're dealing with a unit circle. Now, I don't need to show that division by 1 because anything divided by 1 is itself. So sine of theta is really equal to just y by itself. Therefore, cosine of theta can be established the same way. Cosine of theta would have been the adjacent side, x divided by r. So we can say that cosine itself is x alone. Therefore, when tangent is described as our opposite side divided by adjacent side, we're used to calling it y divided by x, we could just as easily say that instead of y, we'll call this sine, and instead of x, we'll call that cosine. So tangent of theta is not just y divided by x, but it can also be seen as sine of theta divided by cosine of theta. And that's a new identity called the reciprocal identities between tangent and cotangent equivalently. Now, these are fundamental identities or reciprocal identities by definition. We also have three additional Pythagorean identities. These are identities that hold true because of the right triangle that's formed in this angle. For example, sine squared plus cosine squared has to equal the number 1. Sine squared of theta plus cosine squared of theta has to equal 1. And that should make sense to you. If we're saying that sine of theta is y and cosine of theta is x, then y squared plus x squared should equal 1 squared, since our radius is 1. Well, 1 squared is 1, and x squared is cosine squared, and sine squared is y squared. So therefore, that should be easy for us to see this calculation. In a moment, we're actually going to prove this. We're going to use a mathematical proof to show that this will always be true. In a similar fashion, perhaps later we'll discuss it, we have these other relationships as well. Tangent squared of theta plus 1 is equal to secant squared of theta. 1 plus cotangent squared of theta is equal to cosecant squared of theta. Now, you might be wondering, why on earth do we need to know this information? And all that I can tell you really at this point is that it's helpful for problem solving. Perhaps we'll have some pieces of information in the form of tangent, and we need to transform that information into a form related to secant. Well, we can do that with this Pythagorean identity. Or maybe we have information about sine of theta, and we would like to know that information about cosine of theta. We can use one of these identities to help make that transformation possible. Now, this part of the notes is really just a formal way of showing the commentary that I made just a moment ago up here in this part of our box. We need to define tangent of theta in terms of sine and cosine using this diagram. So this is an example of us being able to redefine or transform a value that's written in form of tangent into a form that utilizes two other trig ratios. For example, we know that tangent of theta is defined in this case to be, again, opposite over adjacent. Tangent of theta is equal to y divided by r. But this is tangent in terms of y and r. We want tangent in terms of sine and cosine. And again, since we know that y by itself is equal to sine of theta, because that would be opposite over hypotenuse, we can say that tangent of theta is equal to sine of theta. And since r, oops, that's not right. Tangent of theta is not y over r, it's y over x. Let me get that corrected here. Since x is equal to cosine of theta, again, we have our adjacent side divided by hypotenuse, and our hypotenuse was equal to 1. We now have tangent defined as tangent of theta equals sine of theta divided by cosine of theta. We now have tangent in terms of sine and cosine. For this next bullet point, I'm going to prove the first Pythagorean identity. And that first Pythagorean identity states that sine squared of theta plus cosine squared of theta must equal 1. So when we prove anything using our mathematical tools, that means we have to start with this statement and show mathematically that it is equal to this statement. Now, if we were doing a formal proof like you might see in college, it's not good enough just to prove it in one direction, to say that sine squared of theta plus cosine of squared of theta can be rewritten this way, but you also have to show that this 1 can be rewritten in that direction as well. But we won't go that far for right now. Let's start off with what we know. Sine squared of theta plus cosine squared of theta can be rewritten in a different form. Now, it might be a bit unusual for you to see this, that the squared symbol, if I'm talking about sine of theta squared, we write that square or that exponent right here in between the trig ratio and the angle measure. And to be perfectly honest with you, I've seen this enough that it didn't faze me, but I just now realized that it might be a bit confusing to you. Sine squared of theta is really the same as finding sine of theta and squaring that result, or finding cosine of theta and squaring that result. These two statements here mean the exact same thing as the statements over here on the right-hand side. So what we know is that sine squared of theta, well, sine of theta is really defined as the y value divided by r squared, and cosine of theta is equal to our x value divided by r squared. In the truest sense, this is going to hold true. Now, in our unit circle, we could have substituted the letter r with the number 1. And had you shown that to me here in your proof, then that probably would have been okay for our discussions now. But let's move forward with this, supposing that we're not dealing with a unit circle, but any triangle with any radius. I know that y divided by r squared would be the same as y squared over r squared. And x over r squared is x squared over r squared. The product of x over r is x squared over r squared. Now these two have a common denominator, so I'm going to show that y squared plus x squared, so y squared plus x squared over r squared. And here's where we have to make a mathematical leap. If you think back to the Pythagorean equation, any right triangle, if we have x, y, and r, we know that x squared plus y squared equals r squared. X squared plus y squared is equal to r squared. So this x squared and y squared added together, this piece here is exactly the same as this here, x squared plus y squared. And we know that x squared and y squared added together must be r squared. So I'm going to use this r squared to replace this x squared plus y squared. And now what I have is a fraction, r squared divided by r squared, and you know what happens when I have a number divided by itself. R squared divided by r squared is equal to 1. Therefore, by proof, we've shown that sine squared of theta plus cosine squared of theta through each of these mathematical steps is exactly equal to the number 1. We've proven this Pythagorean identity. Let's take a look at example 5, how we can express one trig function in terms of another. Let's say I have some information about theta in terms of sine, and I need to transform that information into theta in terms of cosine. So we're going to solve part A, and this might actually take 2 parts to do. We know that by the Pythagorean identity that we just proved, that sine squared of theta plus cosine squared of theta must be equal to 1. Now if I need to express sine in terms of cosine, this would be the perfect identity to use because we have both sine and cosine in this single identity. Basically what I'd like to do is get sine by itself. So in order to do that, I could subtract cosine squared from both sides of the equation. And that would look like this, 1 minus cosine squared of theta. Then, in order to get sine by itself, we will take the square root of both sides. Sine of theta, therefore, is equal to the square root of 1 minus cosine squared of theta. Now, don't forget that the plus and minus sign must be included here. So sometimes sine of theta is equal to a positive square root of 1 minus cosine of theta, whereas sometimes sine of theta is equal to the opposite of the square root of 1 minus cosine of theta. So let's think of that diagram that we had just a moment ago, or I should say in the last class. All students take calculus. So if I had an angle measure in either this first quadrant or the second quadrant, then sine of theta should be positive. However, if I had an angle drawn in this third or fourth quadrant, then sine of that should be negative. So we would finalize this by saying something like this. If sine, or I'm sorry, let's say it this way. If theta, the angle, exists in the first or second quadrant, we know that sine of theta has to be positive because all trig functions are positive in the first quadrant and all sine functions are positive in the second quadrant. So if theta exists in the first or second quadrant, then sine of theta must be positive, so that must be the square root of 1 minus cosine squared of theta. However, if theta exists in the third or fourth quadrant, then sine of theta must be equal to the opposite of the square root of 1 minus cosine of theta. Because we know that sine of theta for either angle, either in the third quadrant or in the fourth quadrant, must be a negative number. So to answer part B, we need to express tangent of theta in terms of sine of theta, where theta is in the second quadrant. We have a lot of information to work with here. Well, one of the things that I might remember is that tangent of theta is equal to sine of theta divided by cosine of theta. Now this is almost good to go. We have tangent in terms of sine, but it's also in terms of cosine. So I'd like to get rid of this cosine. As a bit of side work, I'd like to find out what cosine is in terms of sine as well. So just like we saw a moment ago, we have sine squared of theta plus cosine squared of theta, and that has to equal 1. This time I'd like to get cosine by itself. So cosine squared of theta must be equal to 1 minus sine squared of theta. And cosine of theta, after I square root both sides, is equal to either positive or negative square root of 1 minus sine squared of theta. So the question becomes, when is cosine of theta positive and when is it negative? Well, let's go back to that diagram here. All students take calculus. So cosine would be positive in the first quadrant. Cosine would be positive in the third quadrant. Since we were told that our theta value is actually in quadrant 2, we're in quadrant 2 here, then I know cosine must be the negative version of this definition. So I'm going to write tangent of theta not only equal to sine of theta, but also sine of theta over the opposite of the square root of 1 minus sine squared of theta. And I can stop here with that definition. Let's consider another example. This time we'll evaluate a trig function. If tangent of theta is equal to 2/3 and theta is in quadrant 3, find cosine of theta. Let's draw a quick sketch here. Actually, I don't want a unit circle because this hasn't been indicated to me whether we're dealing with radians or degrees. Instead, I can draw a picture of a triangle. So let's say that this is my angle measure. Tangent of theta has to be equal to the opposite divided by the adjacent. So opposite side divided by the adjacent side. We can go ahead and find the missing side length here. 2 squared plus 3 squared has to equal our missing side length squared. So this is 4 plus 9 equals c squared. That's 13 equals c squared. C must be equal to the square root of 13. So with a little bit of side work, we can find out what this missing side length is. Now with all three sides of our triangle identified, we can very easily find out what cosine of theta is. Cosine of theta would be our adjacent side divided by our hypotenuse. 3 divided by square root 13. But we're not done yet because there's an extra piece of information that we have to consider. We know that this cosine of theta must exist in quadrant 3. Theta must exist in quadrant 3. So because of that, we have to recognize where cosine is positive and where it's negative. Cosine's only positive in the first quadrant and the fourth quadrant. So if I have an angle measure drawn in the third quadrant, then cosine must be negative. And I'll say that cosine of theta is equal to the opposite of 3 divided by the square root of 13. Now, there is another way that we can solve this too, and I want to show it to you so that you're at least exposed to both methods. You can decide which one you would like to use. If I remember our trigonometric identity based on the Pythagorean equation, we know that tangent squared of theta plus 1 is equal to secant squared of theta. You might be wondering, well, why is this going to be helpful for us? I thought we were supposed to write tangent in terms of cosine, or write cosine in terms of tangent here. We don't have a cosine in this equation. Well, actually we do, because secant, remember, secant is the inverse of cosine. So if I write this again, tangent of theta plus 1 is equal to 1 divided by cosine squared of theta. Secant squared of theta, the inverse of that is 1 over cosine squared of theta. Now we have cosine of theta. All that we have to do is get this by itself. I could label this now as inverses so that I bring the cosine to its to the upper position here. So I'll raise both sides to a -1 power, and all that does for me is it creates a fraction on the left side, 1 divided by tangent of theta plus 1. I'm sorry, tangent squared of theta plus 1, and that's equal to cosine squared of theta. Now in order to get cosine by itself, we can find the square root of both sides. And I'm going to spread some things out and make sure that I have enough room here. So cosine of theta is now equal to the square root of 1 divided by tangent squared of theta plus 1. Now we can just make some substitutions and finally identify what cosine of theta is. We knew that tangent of theta was equal to 2/3, so therefore cosine of theta is equal to, again, the square root of 1 divided by, now we're not going to look at this as tangent squared, but rather 2/3 squared plus 1. And cosine of theta, if we use some algebra here to simplify, we have the square root of 1 divided by 4/9, because 2/3 squared is 4/9, plus, I'm going to write this as 9/9 so that we can combine those two fractions. Cosine of theta is the square root of 1 divided by 13/9. And when I have 1 divided by a fraction, then I can rewrite that as the not 13 over 9, but now 9 over 13. I want the square root of that. And cosine of theta then is equal to the square root of 9 over the square root of 13, which is 3 divided by square root 13. And while we think we might be done here, please remember that we are dealing with an angle measure of theta inside the third quadrant. All students take calculus. Cosine is only positive in the first and fourth quadrant, so when I have an angle measure in the third quadrant here, this must also be negative. And I guess truthfully we should have indicated that all the way back here. We should have shown that we had a positive or negative option for our answer. All along the way here, since we introduced this square root sign, we should have introduced the positive or negative option there. We could have settled on negative at the very end because we know that the theta angle has to exist in the third quadrant. Now in the interest of time, I'm going to stop the video here. It's been quite long. We only had one more example to walk through. So I'll talk about this perhaps first thing tomorrow, and we'll continue our discussion. I want to be able to answer any of the questions that you have before we move forward.